Hello. Okay, we are starting. Yeah, this is the session on secure computation. So we have four talks in this session, and the first talk is going to be about single input functionality against dishonest majority, practical and round optimal. And this is by Xie Xiao, Bingxian Xiang, Hongxian Xiao, and Kui Lin. And Xie is going to give the talk. Please.
Thanks for the introduction. Okay. Hello everyone. This is Zhe Zhou, and I'm a PhD student from Zhejiang University. The topic I'm going to share today is single input functionality against the dishonest majority, practical and round optimal. And this is a joint work with Bingsheng Zhang, Hongsheng Zhou, and Kui Ren. Okay, how to? Okay. Multi-party computation, short for MPC, is an important cryptographic primitive. It allows a group of people who are distrustful of each other to jointly compute a given function. In an MPC protocol, each party has a private input, and there are two basic security requirements of an MPC protocol. That is, first, each party will get the correct result as the output, and second, each party's private input should not be leaked to other parties. And the single input functionality, short for SIF, is a special case of MPC, where only one distinguished party, who called the dealer, has the private input, and the rest parties, who called the verifiers, do not have any private input. And in a secure SIF protocol, each verifier should also get the correct result as the output, and meanwhile, the verifiers cannot learn anything beyond that result. Indeed, SIF is less popular than MPC, but it is still important and has many applications, such as multi-verifier zero knowledge and verifiable relation sharing, and these two primitives will be explained later. And in this talk, my presentation will be divided into three parts: background, construction, and discussion and conclusion. In the first part, I will give you more details about the applications of SIF. Then I will raise our research question. And in the second part, I will show you how we construct the first one-round practical SIF protocol in the pre-processing model against the dishonest majority. And I will also provide you some experiment results that illustrate the practical efficiency of our protocols. Finally, I will bring up some discussion and make a short summary. Okay, now let us move to the first part. As I mentioned previously, SIF indeed implies two primitives, namely MVZK and VIS. In an MVZK protocol, there is a prover and multiple verifiers, and it allows the prover to prove the statement to all the verifiers at once. And in a VIS protocol, it is more complicated. There is a dealer and multiple verifiers, and it allows the dealer to share its holding secret to the verifiers at first, and meanwhile, it allows the dealer to convince the verifiers that their shares satisfies an NP relationship. And in real-life applications, SIF, VIS, and MVZK can also be deployed in some real-life application scenarios, such as private aggregation system, verifiable secret sharing, and distributed key generation. Given SIF is important, a lot of research on SIF has already been done, and I list some of them above. As you can see, these works can be divided into two categories. And the first category of work can achieve one-round online communication. So they are round optimal in the pre-processing model. However, they are only feasibility results, so they are not practical at all. And the second category of these works can offer practical efficiency, but they all require more than one round online communication. Therefore, it is very natural for us to ask, is it possible to construct a practical SIF protocol with merely one round online communication? And in this work, we provide a positive answer to this question by constructing the first SIF protocol that is practical, round optimal, and can support optimal corruption threshold. Okay, Now let us move to the second part, construction. And first, I will show you the insights of our protocol construction. We first observe that previous work that offer practical efficiency or follow the similar online communication pattern. That is, the dealer will first deliver the result and the proofs message to the different verifiers in the first round. And in the following rounds, the verifier will communicate with each other to check if the received proof message are correct or not. And since the verifier has to perform the consistency check after receiving the message from the dealer, therefore all the previous work that offer practical efficiency require more than one round online communication. And in this work, our key observation is that the consistency checks among the verifiers could be pushed into the pre-processing phase. Therefore, it is possible to reduce the online communication round. Okay, and here is our construction overview. Since we are dealing with the pre-processing model, so our protocols can be divided into two phases. And in the pre-processing phase, we try to extend the vector oblivious linear evaluations, short for VOLE, from two-party setting into the multi-verifier setting. And in the online phase, we try to extend the non-interactive multiplication protocol based on VOLE into those based on multiple verifier VOLE. Okay, so let us recap what is VOLE. VOLE, which is also known as information theoretical MAC, is a widely used two-party primitive. It allows party 1 to hold a message and hold the corresponding MAC tag, and allows party 2 to hold two MAC keys. One of the MAC key will be reused for multiple times, so it is called global MAC key, and the other MAC key is called local MAC key. If the party 1 wants to open her holding message to party 2, she can simply send the message and the corresponding MAC tag to the party 2, and the party 2 can use the equation above to check if the received message is correct or not. And it's easy to see that VOLE has three basic security properties, namely hiding, binding, and linear homomorphism. And in this work, we try to extend VOLE from two-party setting to the multi-verifier setting. That is, we let each verifier hold a distinct global MAC key, and the dealer's message will be authenticated to all verifiers at once. And we note that in RS-22, the authors also proposed a similar primitive, but the protocol constructions are different. Okay, so here we will provide an overview of our protocol constructions. In the first step, we let the dealer to run VOLE protocol with different verifiers using the same input. And then in the second step, we let the parties to perform the consistency checks to convince the verifiers that the dealer has used the same input. And our consistency checks avoids the usage of commit and open procedure in RS-22. So our consistency checks requires less communication rounds. Okay, now here is the detailed protocol constructions. Let row 1 and row 2 be the protocol parameters. We first let the dealer to pick a random vector whose length is row 1, and this random vector will serve as a mask to prevent potential leakage in later steps. Okay, so then the dealer can concatenate the random vector with her input vector, and the resulting vector is denoted as x prime. Then the dealer can use x prime as the input to invoke different VOLE protocols with different verifiers. And then the parties can jointly perform the consistency checks for row 2 times. And in each consistency check, the parties will first jointly generate a random vector, then compute the inner product of this random vector and their VOLE correlations. And finally, the dealer can broadcast the computed result and send the corresponding MAC tag to the verifiers. And the verifiers can locally check if the received message is valid or not. And we suggest that this protocol could be viewed as a generalization of WRK17 protocol, where WRK17 protocol only focuses on the Boolean circuit case, while this protocol can be applied to both Boolean circuit and arithmetic circuit if the parameters are chosen properly. Okay. So we have introduced the MVVLE, which will be generated in the preprocessing phase, and in the online phase, the parties can consume the random MVVLE correlation to speed up the online communication procedure. And since MVVLE also has a linear homomorphism property, so it is easy to handle the addition gates. So in this slide, I will mainly focus on the multiplication gates. Okay. Imagine there is a multiplication gate with the authenticated input alpha and beta and the authenticated output gamma. And we observe that the party's information actually satisfies the equations above. And this bj could be viewed as a polynomial with delta j as the independent variable. And we can further observe that the coefficient of the degree 2 item should be 0 if the dealer is honest, since it is a multiplication gate. Okay, and furthermore, the coefficients of the degree 0 and degree 1 items can be locally computed by the dealer itself. So the dealer can compute these coefficients and send them to the verifiers, and the verifiers can locally compute bj and using the equation above to check if the received message are correct or not. And all the multiplication gates can be handled together. So that's why we can achieve one-round online communication. And this protocol can be viewed as a generalization of DIO21 and YSWW21. Okay. Finally, we make some experiments to compare with related work. We first compare with our previous work that published last year. As you can see the picture above, this work's running time and communication cost are both better than our previous work. This is mainly because that our previous work used the heavy BDOZ style preprocessing protocol in the preprocessing phase, while this work utilized the highly optimized VOLE generation protocol in the preprocessing phase. And we also compare with the concurrent work, namely EPSW24, when the number of verifiers is set to be 8. As you can see the table above, actually our end-to-end running time is slightly worse than EPSW24. This is mainly because that they used a technique called packet secret sharing. And due to the usage of packet secret sharing, their communication complexity can be independent of the number of verifiers, while ours cannot. On the other side, as you can see, also due to the usage of packet secret sharing, their corruption threshold is actually worse than ours. So I think it may be kind of trade-off between the corruption threshold and the communication complexity. Okay, finally, let us move to the third part, discussion and conclusion. Someone may notice that our work should require broadcast channels to enable one-round online communication. Actually, all the existing one-round SF protocols all require broadcast channels to enable one-round online communication. Since broadcast channels are more expensive than regular communication channels, it is very natural for us to ask, is it possible to construct a one-round SIF protocol without broadcast channels? The sad truth is that in this work, we found the answer to this question is negative. The intuition is simple. Since SF implies MVZK, and MVZK has a consensus property which is impossible to achieve within one round when broadcast channels are not available. And so as the SF. And I will provide you a simple example to illustrate the reason why. Imagine there are only 2 verifiers in total, and we let the adversary to corrupt the prover. And the malicious prover will prepare 2 distinct witnesses and use this witness to generate distinct proofs message and delivers them to the different verifiers. As a result, the verifiers will output distinct results that breaks the consensus property of MVZK. And since MVZK is a special case of SF, so this impossibility can be easily extended to SF itself. So we prove that a one-round SF is impossible without broadcast channels. Okay, so in this talk, I we constructed the first one-round SF protocol with practical efficiency in the preprocessing model, and we also proved the necessity of broadcast channels for building one-round SF. And finally, I came up with some interesting future directions that may deserve further investigations, such as constructing a one-round SF that has merely OC communication complexity. And it is also interesting to explore more real-life application scenarios of SF. And finally, I think it is important to reveal more connections between SF and other useful cryptographic primitives. And that's all. Thanks for your listening.
So thank you for your talk. Is there any questions? Okay, while you're thinking about the questions that you're going to ask in just a minute, maybe I can ask one. It seems like, or you mentioned one of the related works, this three-round protocol that you...
Yeah.
And in your comparison, you mentioned that it was slightly faster?
No.
Or did I misunderstand what you were saying?
Okay, sorry. I was trying to say that compared to this related work, EPS W24, actually our running time is slightly worse than theirs. Oh, this is mainly because their communication round complexity is better than ours, since, as you can see, their communication complexity is independent of the number of verifiers. Okay, but ours does. Okay, so this is the main reason why their end-to-end running time, includes the communication time, are much better than ours. And this is mainly because they use the technique called packet secret sharing. And also due to the usage of packet secret sharing, their corruption threshold is worse than ours. So I think it is a trade-off between the corruption threshold and the communication complexity. If you want a stronger security, namely if you want a better corruption threshold, you have to give up that technique, I think.
Okay. Yeah. Okay, thank you.
Okay.
Are there any other questions? If not, let's thank the speaker again.
Thank you. Okay, let me just...
So our next talk is titled Securely Instantiating Half-Gates, Garbling in the Standard Model. And this is by Anasuya Acharya and Karan Asari, Mirza Ahad Baik, Dennis Hofheinz, and Chetnan Kamat. Yeah, so Anna Shuya will give the talk.
Okay, hello. Thank you for the introduction. And okay, so this work is not just about half-gates, it's about a whole category of garbling schemes that allow for the free XOR optimization. I'll explain what it is in a bit. And we prove the security of these schemes in the standard model. This builds very heavily on prior work, so I guess the first half of the talk is going to be on what garbling is, how to prove its security, what this optimization is, and all that. And the second half is going to be about what we actually do, so like, hang in there, please. So, okay. Fine. So first we start with what garbling schemes are. So in very layman terms, this is an object that allows us to take a secret input and evaluate a function on it so that only the function output is revealed and nothing else. So how does one garble? So think of it as, okay, if you have this input and function in the clear, think of like a parallel encrypted domain. So, and you have this garbling algorithm that takes in the function and outputs a function encoding, which is popularly called the garble circuit. And this garbling algorithm also outputs two more things. One of them is this input encoding information. So this is something that you can take with the actual function input and convert it into this encoded sort of input, which hides the input completely. So given the encoded input, you can't say what the actual input was. Now, given this input encoding and the garbled circuit, you can run this through an evaluation algorithm and get the encoded outputs. So till now, we're still in this encrypted domain. And now what happens is, with this encoded output, you can map it back to the function output using this output decoding information. And this is how garbling schemes work. So how do you actually garble? Well, you take the function and you first convert it into like a Boolean circuit with binary gates. And these gates are going to be AND and XOR gates. This is how you traditionally garble. There are a lot of other ways of doing it, but yeah, this is how it was done first, and people kind of followed what they did. So yeah, so we'll first look at how garbling first started by Andrew Yao happened. So yeah, so you take each of these gates and then you look at like the gate functionality and you garble each gate separately in a sense. So say we have the AND function and here's the truth table of the AND gate, and now we are going to row by row encrypt the truth table in a set of 4 ciphertexts. All right, so how this is going to work is, say you have the input wires are, say, A and B, and an output wire C. You sample a label for the 0 semantic value and the 1 semantic value of each wire. All right, and then what you do is you encrypt the output wire label using the input wire labels as the keys, and that's it. So, and this set of 4 ciphertexts becomes the garbled AND gate. Now, when you're evaluating, what happens is you don't have both labels. The evaluator only has one label. It has the label corresponding to the actual input value. And so if you have one label for each input wire, you can decrypt only one of these 4 ciphertexts and get one label for the output wire, and this invariant kind of continues till the output, till the circuit output, and then you can decode back the final output. So this is how garbling is done, and this is kind of neat because this is very efficient. It uses symmetry key primitives like encryption, right? And like, so you can garble fast, you can evaluate fast. The only thing you can't do nicely is communicate the garbled circuit because it is big. It's as big as the function size. So the one thing that people have been trying to do for a long time now, after Yao invented or discovered, or rather designed garbled circuits, is reducing the size of the garbled circuit. So, and in doing that, the first big sort of breakthrough that came out was, like, a lot of people have done a lot of things before, but this is was one of the wow results, okay? So this is free XOR. So Kolesnikov and Schneider in 2008 came up with this. This is to say that now you still need 4 ciphertexts, 4 kappa bits to encrypt an AND gate, but XOR gates, you don't have to communicate anything for them. So how you do this is to basically say that, okay, for every wire, we are still sampling a 0 label, but we don't sample a 1 label at random. We sample a global label delta, and we say the 1 label is going to be the 0 label XORed with delta. And that's how you do it. Now, why does this get rid of the XOR gate? It's because now what happens is if you have, so in the XOR gate, the output wire labels are computed as a function of the input wire label. So you use the 2 input 0 wire labels, XOR them, and you get the output wire label for 0. And the 1 label is going to be that XORed with delta, and that's it. And how do you evaluate? For whatever 2 input wire labels you get, you XOR them, and that's your output wire label. The deltas cancel out, and it gives us this nice structure. So that's free XOR. Now that you have this, the security of free XOR kind of relies on the fact that delta is something that only the garbler knows and the evaluator does not. Because if it does, it can find the other label and security breaks. So now a lot of subsequent work has happened after this, which has tried to preserve free XOR and also reduce the size of the AND gate. So one of them is this 2 halves garbling scheme, which basically gets from 4 kappa bits for AND gates to 2 kappa bits. And so it's involved. It's not as simple as just row by row garbling the truth table, like encrypting the truth table. But here are the two main ideas underlying the scheme. One of them is they don't do encryption like an encryption scheme anymore. What they do is they use a hash function. So you take a hash function, you hash an input label, and you use the output to mask the output label. So that's how you do it, and you don't, and you do it separately. You hash the label for wire A separately and the wire B separately, and that's how, and that's that. And also, as a result of what they do, the output labels of the AND gate also becomes like a function of the input labels. And further after this, so people thought 2 halves was great and all, but even after that, a lot of people, like, they pushed it further, and now we have this 3 half scheme, which says, okay, now you don't even need 2 whole ciphertexts to garble an AND gate. You can do it a ciphertext and a half. So that's 3 halves. And then further, like just last year, there was this new arithmetic garbling scheme that Heath came up with, which uses similar optimizations, and they can now garble arithmetic gates like plus addition and multiplication instead of doing binary circuits. So all of these schemes are cool, but then they have this one underlying common denominator, which is they require a hash function which has some circular security property. And we look at what this property is like right now. So this is called the circular correlation robustness, or CCR for short. And what this says is that, okay, there is this hash function which takes as input a label, basically, and an index. This index is kind of like a counter, and then it outputs something of the same size of the input, basically. So you have the inputs from 0, 1 to the kappa, and you have outputs also of the same size. And now you have an adversary that only has oracle access to this hash function. And it also has oracle access to something else. This is this orange box over here. This orange box can either be the random oracle, meaning for whatever xni you give it, it'll give you a random output. Same xni, same output, but yeah. Or it can be the CCR oracle, which says that, okay, there is this hidden delta that only the orange box knows. And if you give xi and a bit b, then it's going to hash x XORed with delta, and it will decide whether or not to XOR delta to the output of the hash, depending on what value b takes. So that's what this orange box is. So that's the CCR oracle. And the security game is that this adversary with access to both of these, with H and O, needs to say what the orange box is. Is it the CCR oracle or the random oracle? That's it. So if you have, so with this security game, so it's kind of, so there is one tiny technicality over here, which is there is an easy way to break the security game, right? I mean, you can just say, okay, I'm going to take x and I, and I'm going to query the orange box on xi0 and xi1. I will find delta, and it breaks. So the security game says that you can't do that. So so the legal set of queries are a set of queries where you can't query xi with 2 different b's, the same xi with 2 different b's. And that's this. Now, how this is used to prove garbling security is, well, you have this garbling adversary right now. Its job is to, so this is someone that can distinguish between a simulated garbling and a real garbling. And so for that, we need to go into a little bit of detail as to how a simulated garbling is made. So simulated garbling is basically to say that, okay, we are going to create a garble circuit while keeping in mind what the evaluator would do to evaluate the garble circuit, yeah? So we kind of saw in the toy example of Yao's garbling that, the garbler creates 4 ciphertexts, evaluator only touches 1 of them, right? And so think of it right now as, now we are going to create 1 label for each input wire and not the other label at all. And then when we're creating the garbled circuit, every time we have enough information to use the hash function, like we have a label that goes into the hash function, we are going to use the hash function, the gray box. Every time we don't, we are going to use the orange box. We are going to sample something completely random and put it as the hash function output, and that's it. And you create the garbled circuit just like that, and that's the simulated garbling. So how you can reduce indistinguishability of a real and simulated garbling to a CCR or security is obvious. The garbling adversary basically gives the circuit and the input to the CCR adversary. And this adversary is now going to use H for everything that the evaluator can know, and use O for everything the evaluator cannot know, and create this garbling, right? And this it's going to give back to the garbling adversary. So F is the function garbling, D is what you need to decode the output, and X is the set of labels that the evaluator is allowed to see. All right, and now when the garbling adversary says, okay, real or simulated, the CCR adversary can map it directly back to, say, CCR or random oracle, and done. So that's how you would use this for a security reduction. So this is, up to here, is something that already exists. This is how you would reduce garbling security to CCR security. And here is what we do. Note that in CCR security, the adversary is not allowed to have the hash function. It's only allowed to have like oracle access to the hash function. In the real world, what happens is we assume that, okay, random oracle hash function can be instantiated with SHA or fixed key AES, and we give the function to you and hope it works. And now the goal over here is to say that let's try to not do that. Can we get away with not doing that, right? So for that, what we say, so the first thing we do is we define another security assumption, which we call weak CCR. And this is a non-oracle assumption. I mean, notably, what happens is we define a security game, and at the end of the game, the adversary gets to see the hash function description and then decide based on it. So that's this game. And then we show that even based on this security game, all the garbling schemes, these free XOR-based schemes that I've talked about, they're actually secure even assuming weak CCR. And then we show that, so the second part is to show that, okay, weak CCR can actually be instantiated. And I mean, yeah, it's a feasibility result. We instantiated with IO and PPRFs. So this is puncturable PRFs. Okay, so first, we describe what weak CCR is. So here was CCR. How does this change to get weak CCR? First of all, the adversary does not have oracle access to the hash function. So now we have a challenger. This is a challenger adversary game. The challenger, now you have the adversary that only talks to the challenger, and it gives the challenger a query strategy. A legal query strategy is basically a PPT algorithm that encodes how the adversary wants the challenger to query H and O. And and it can only query O using legal query. So anything that a CCR adversary could do using H and O, a weak CCR adversary can encode into a query strategy. So plain, right? So that's here. But I mean, even if that's the case, I mean, weak CCR and CCR are not equivalent because the challenger has like non-black box access to the query strategy. So, okay. And then, so the challenger is going to like basically run the query strategy, and it will then output the hash function description and all the queries that were made to the orange box along with their responses. And then the adversary gets to say whether it was a CCR oracle or a random oracle. It only has to get from the, only has to say about the orange box, looking at the query the response of the query strategy. And now, how this is different from CCR? Well, the adversary does not have access to the hash function, but it gets the description in the end. And well, it's also different from a related notion called RTCCR, randomized tweakable CCR. This was a notion that was used to prove security of the 3/2 garbling scheme. The main difference is that they used a hash function where the input and the output lengths were different. And you need more than just one bit B to decide whether you want to XOR delta to the output or not. You need some linear combinations going on over there. So there is that. Now, how you would use this to prove security is, well, obvious. You have the garbling adversary. It sends the circuit and the input. Weak CCR now creates a garbling query strategy. Basically, everything that it would have done to query, it sends to the challenger. The challenger sends back the list of queries. Adversary redoes the garbling, sends it back to the garbling adversary, and now it replicates its answer, and done. Now, how would you construct weak CCR? Well, we use two building blocks. One of them is indistinguishability obfuscation. It's to say that there is a PPT function that takes in for two different representations of the same function. It can output something from which you can evaluate the same function, but you can't say what circuit representation it came from. And the second building block we use is a puncturable PRF. So this is a PRF that you can run on two different kinds of keys. One is like a normal regular key, and the other is a punctured key, which is with respect to some particular input, such that, okay, if you are evaluating the PRF on keys on the inputs that are not punctured, for both keys you'll get the same output. If you are evaluating on the punctured key, however, punctured point, then what happens is you will get outputs that are different, but it'll be indistinguishable from random. And how you combine them is kind of obvious. Like you basically hard code the key into the the PRF, and then you obfuscate it, and that's it. So this may look very obvious, and this was where we started to begin with, and then we tried to prove it, and the proof didn't. It took a while for the proof to go through. So, yeah. So what we have to prove over here is the fact that if you have this hash function and a query strategy made using the CCR oracle, if you switch out the query strategy for the random oracle, you can't tell the difference, even with the same hash function. We do this using two steps. One is basically you move from the query strategy from the CCR to a set of queries and outputs where the outputs are all random strings. And now what you do is you change the hash function to have this to have the punctured key in the PRF, and the PRF is punctured on all the points that the query strategy was queried. That the orange oracle was queried on, essentially. And now, so this move is basically just reducing to PPRF security. Now from here, we need to say that if we go and we switch the hash function back to having the original key, the non-punctured key, you really can't tell the difference. And from there, you can say that, okay, the output of the query strategy is basically the same as the output of the random oracle. So, yeah, okay, so the basic argument to go from hybrid 1 to 6 is just to say that you can, so since the adversary who has the hash function description does not know delta and it's hard to compute, it really can't say what points the hash function was punctured on, and so it really doesn't make a difference what key was used in it. So, yeah, I'll probably skip through this because we don't have time. This is just to say everything that so from hybrid 2 to 5, you're trying to get rid of the delta in it, and then from 5 to 6, you switch back to from punctured key to non-punctured key, and you're done. And this is it. So here's some concluding remarks, essentially. One of them is the fact that what we have is strictly a feasibility result. We use I/O, so it's not exactly super efficient. This is just to say that all these state-of-the-art schemes are also secure in the plane model. The second thing is, since we can get weak CCR from I/O and one-way functions, this does not imply collision resistance. So it is actually pretty weak. The third thing is, well, yeah, this is just some future directions. This is to say that, I mean, it's still open to see if we can instantiate weak CCR from, something that is not I/O. And also, it's still an open question to say if we can prove adaptive security of these schemes in the plane model based on a weak CCR, because you can't really do it based on CCRs, black box and CCR. And that's it. Thank you. That's all I have. I'm sorry.
Thank you very much for your talk. I'm afraid we have to skip the questions, but I'm sure you will be here in the break to answer any question people might have. So
sorry.
yeah, no, that's perfect. Okay. So the next talk is titled Efficient Permutation Correlations and Batched Random Access for Two-Party Computation. And this presentation is going to be given by Stan Piscini. And it's joint work with Srini Raghuramaraman, Peter Rindel, and Harshal Shah. So please start the presentation.
Okay. Thanks so much for the introduction. So in this talk, I will present efficient permutation correlations and batch random access for two-party computation. And it's done by myself and my co-authors, Srini, Peter, and Herschel. And my hope is that by the end of this presentation, we will all understand the value of permutations to MPC. So the motivation for this work is array access in secure computation. And array access is a standard primitive. It takes as input index I, some array A, and it outputs the array entry at index I. Now we're specifically interested in the setting where this index I can depend on some secret program input. And it is the case in many real-world applications. And while in plain text, array access is a very simple constant time operations. In MPC, it's often the bottleneck of secure computation. And the reason is that the array access must remain hidden. So revealing something about the index I could reveal something about the input to the computation. And there are ways to do it in MPC. One naive way would be to do linear scan, in which case, let's say we want to access this index I. We simply go through the full array. When we get to the array entry we want to access, we save it, and then we output it. And basically, the issue with this approach is that to access a single element, we need to go through the entire array. On the other hand, the constants are low. But the question is, can we do better? And there's a line of work on oblivious ORAM which achieves that, but basically each access requires some polylock overhead. And while that's better than linear overhead, we incur high constants. And we don't want that. So while this landscape that I'm showing here is a little simplified, the, I guess, primary two directions for oblivious ORAM were either some secret sharing schemes or garbled RAM. And if you look at the secret sharing schemes, they have some disadvantages. So if you want multiple accesses, they often require to do them sequentially, and that can add polylock rounds. Then on the other hand, the garbled RAM, which works with garbled circuits, is constant round protocol, but on the other hand, it incurs this kappa overhead. And simply because while oblivious RAM got much better and much more efficient, in many settings it's still prohibitive. And because of that, some works looked into RAM access that's done in a batched manner. So what I mean by that is, let's say we have some array A. We also input some selection function sigma, which tells us which indices we want to access, and then it outputs all of them in A sub sigma. And now, this talk is about permutations, and I just want to show that that basically, if the selection function, if all the indices are unique, we get a permutation, and then A sub sigma is the reordering of A. And this basically should give us a hint that maybe if we have permutation, it should allow for some more complex batched RAM access if we use some extra primitives. And yeah, and in this talk I will show how we can get that. And in fact, we will implement some gates which are similar to the standard ORAM gates, and they require amortized O1 overhead per access and are concretely very efficient. Okay, so now let me just briefly summarize our contributions. So we introduced a suite of two-party semi-honest protocols. So we present two novel permutation correlations, which I will get into what that means. Then we present some expressive batched RAM read and write gates. And then we present a toolbox of algorithms that basically show how the permutation correlations can be de-randomized and give some applications to really show how powerful this primitive is. And in this talk, my focus really will be on presenting one of the novel permutation correlation protocols, and then also showing one of these expressive batched RAM gates. Okay, so just what is a permutation correlation? So in a permutation correlation, the Bob inputs some permutation pi, and the functionality output is that we get a secret sharing of some vector A permuted by pi, and basically the ABC are random here. And one way like we should think about it is that this is like a permutation equivalent to like, random OLE or Beaver triples in MPC. And just to be clear, this permutation correlation concept is not novel. It was in this work by Chase et al. And was called shared translation. Okay, so let's get into the two novel protocols. So just to summarize, so there's one weak PRF-based protocol which runs in for an array of size n and L-bit strings. It runs in O of NL communication and 3 rounds, and it runs for 1 million elements. It runs in 7 seconds and communicates roughly 180 megabytes. And just to be clear, so about 6 seconds out of this are pre-processing things, and if done in parallel, let's say we run them on 4 threads, it goes down to like 3 seconds. And I will give the weak PRF protocol in more detail. It's very simple. Then we also give a BCG-based protocol, which is much more complicated, and I will not get into this talk. But it is a sublinear protocol, and in the sense that it runs in O of n log L communication. But it has higher constants, so unless the bit string L is large enough, probably the weak PRF is the right option. Okay, yeah. So just just to get some summary, what weak PRF is, right? So there's Bob inputs some input X, Alice inputs some key, and in our specific setting, we're interested in weak PRF where the output is secret shared. And since it's weak PRF, so the input X is random, and because we're working in MPC, we're really interested in some primitives that design a PRF that's efficient in MPC. And our implementations, in fact, use this both low MC, which is by Albrecht et al. From Eurocrypt 15, and then the more recent alternating moduli by Alamati et al. From Crypto 24. Okay, so as I said, this protocol is actually extremely simple. So I'll sample some key k, and it defines a vector A by simply running, like setting each element of I to fk of I. And then to get the permuted, to get the permutation is simply Alice inputs the key k to the PRF, whereas Bob inputs, because he holds the permutation, he can input pi of I, and they will get the secret sharing pi ci, which is actually the permuted A. And we do it for all 1 through n. And yeah, we get the permutation. And yeah, just one thing to note here, because we're using weak PRF, so the input should be random. So in fact, we run it through a random oracle, and yeah, we get the final form of the permutation correlation. Okay, and just to get an idea, so our focus is really on concrete efficiency. So as I said, ours runs in roughly 7 seconds and 180 megabytes. There were some other works that also try to work on permutation. So for example, the work of Chase et al. From HACRIT 2020. They give a solution that's based on the Benesch permutation network, but they run roughly in 40 seconds and 4 gigabytes compared to us. And then there are also AHE-based solutions. So for example, based on Paye, or also the lattice-based Gazelle by Juvekar et al. And while their communication for Gazelle is roughly similar, the runtime is like 40x larger. And yeah, in fact, this number doesn't, for Gazelle, I just want to know this number also does not include the cost of noise flooding. So in fact, it would be larger. Okay, so let me get also into the batched array access, which was the motivation for this work. So we provide 2 gates, batched read and a batched write. And I just want to clarify, so we allow multiple reads and writes to single index. And when we write, we can just use some associative function to get the final write value. And just before getting into the protocol, so the dominant cost will be secure sort, and yeah, and as I said, we can do accesses with amortized O1 overhead. And just to get a flavor, again, we stress concrete efficiency. So to do an access to 60,000 size array takes roughly 10 seconds and 160 megabytes. So one primitive that will be needed to give this batched RAM gate is this aggregation tree by Badrinarayanan et al. From CCS 22. And just to summarize what it is, so we have some list of blocks and a list of control bits. B are the block, C are the control bits, they're secret shared. And this control bit C, they partition B into sublists. And it partitions it in such a way that whenever, let's say we're parsing the control bits from left to right, whenever we arrive at 0, that's the start of a new block, and the block continues until the next 0. So in this case, we have three sublists, B0, then B1 through B3, and then B4 and B5. And while the aggregation tree technique is more general, how we want to use it is that basically the first item of each sublist is copied into the rest of the sublist. So for example, B1 through B3 will become B1, 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 and B4 through B5 will become B4 and B4. Okay, so let's get into the actual protocol. So let's say we have this array A, and we want to access indices 1, 4, and twice the index 6. And so how would we go about that? So we have four accesses. So we will extend A with 4 dummy blocks that can have any kind of value, and they're in gray. Next, next to this array extended with dummies, we will append these indices. So for A, it's 1 through 6. They're the original indices. And then for the dummies, we will actually put in the indices we want to access. So 1, 4, 6, and 6. And we will extend this array with additional bits. And they will be all zeros in the original array and all ones in the places where we want to make accesses. And now what we do, we will use stable sort using the indices on the left. And just to be pedantic, what it will do, it will return a sorting permutation, and then we will permute with pi. And also the sort itself uses our permutations. Okay, so this is after the sort, and what we now notice is that basically the elements we want to access, they're always followed by these dummies to which we want to copy the values. So basically above 6, we have the two sixes that we want to access. And so somehow, like now we want to copy the green one into the 2 grays above, same with the purple one and the red one. And we can use aggregation tree for it. So how we can use aggregation, we have this list of blocks and also these control bits. And the control bits now, because the control bits were 1 for all the dummies, so they will be part of the same block as the things that just preceded, which we want to access. So basically, these are the blocks for the aggregation tree. And now, when we run the aggregation tree, after that we will copy all the elements in where we want. And basically now, okay, we still don't know where these. This is all oblivious, so we don't know like where the accessed elements are. But however, again, the permutations are powerful, and we can basically unpermute what we permuted. So we can unpermute with pi inverse, and in the end, we will have the accessed elements again at the top. So yeah, it's a very simple but very efficient way to get batched random access read, and a very similar thing works for the write. And yeah, let me just quickly summarize. So there's also some toolbox. So this is a bunch of protocols where we show how permutations can be used. Some of them are novel. Some of them should be more thought of as a systematization of knowledge. And basically, it's a variety of ways in which you can de-randomize the permutation correlations, such as we want to choose the input or the permutation, or the input list is secret shared. But we can also get many permutations with just one correlation, and also using correlation permutation for pi, we can also get the inverse permutation. Then we also give some additional protocols. So the permutation might be either in additive or composition secret sharing, and we give conversions between them. And the different protocols that we give, they might use either. And also then for more concrete applications, we give some sorting and also extraction protocols. Okay, so just to give some summary, so we give a suite of two-party semi-honest protocols. We give some novel protocols for permutation correlations, show how they can get some expressive batched RAM read and write gates, and also give a toolbox of different protocols to understand how permutations are useful for MPC. Thanks so much.
Thank you very much. Is this on? Yeah, okay. Thank you very much for your talk. Is there a quick question that anybody want to ask? No? Okay, let me ask a very quick question then. This is for the semi-honest
Yeah,
case.
this is for semi-honest.
How about the maliciously secure?
So I'll leave that for future work, but from the amount, I don't think there's anything really prohibiting this from being done in the malicious setting. But yeah, it's should be doable, but yeah, I'll leave it for future work.
Okay, yeah. Let's thank the speaker again.
Thanks so much.
Okay, so we have arrived at our last talk of the session, which is titled. Oh yeah, I think you pressed. If you. So the talk is titled Pi, a unified framework for computational verifiable secret sharing. And this is by Karim Bakri. And yeah, please go ahead and give your talk.
Thank you very much. Thanks for the introduction. Hello, everybody. I am Karim, and I'm a postdoctoral researcher in COSIC, so working on applications of zero-knowledge proof. And today we will show that verifiable secret sharing is also one application of zero-knowledge proofs. So I assume that you are familiar with Shamir, so we want to share a secret such that T+1 parties will not be able to learn, will be able to reconstruct, but T parties will not be able to learn anything about the secret. So, but the problem with Shamir, I skipped this part because it's a basic math from high school that you encode to the polynomial of degree T, and any T+1 parties can reconstruct. But the problem with Shamir is that you need to have this trusted party. So the verifiability just tries to remove this trust. So, the well-known and famous protocol, which is widely used in threshold protocols proposed by Feldman, which says that let's first do the Shamir. Then basically you commit to these coefficients of this polynomial by discrete logarithm. Then because it's additively homomorphic commitment, then given the shares, anyone can use this relation to check this well-formedness of the shares. So in checking if there was a complaint, so basically this guy raised a complaint and the dealer has to open this share and the others basically verifies this and they reach the consensus who is malicious, the dealer or the verifier, and they disqualify it. So in the reconstruction phase, basically parties publish their shares and we start to check them by the same proof that we had, and then we collect at least T+1 valid ones and we use them to reconstruct the secret. The problem with the Feldman scheme is that it requires high entropy secret, so you cannot share your email. So to solve this, Peterson proposed his well-known and famous perfectly hiding commitment, which basically says given two generators, you can basically use this one, G power F and H power R, and you achieve basically perfectly hiding, and you can, let's say, commit to even your email, low entropy messages. And to solve this problem, basically Peterson said, let's do Shamir twice. So basically you have another one, so you exactly do Shamir twice. But instead of committing to coefficients with discrete log, you do it, basically with two generators, G power F0, H power R0, and so on. Basically this F0 and R0 are the first coefficients, and these are the others. So again, you publish this as a proof. So they don't call it proof, but we usually show that it's a proof. But it's a proof that is distributed between multiple verifiers. So then given these shares, again, you can check it, similar to the Feldman, nothing has changed, just you do it with two bases, generators. Then again, if there's a complaint, they publish it and they check it. So finally, again, in the reconstruction, instead of publishing just one FI, you need to publish both of them such that we can again run this one and check and collect the valid ones and reconstruct the secret. So this was basically long, standing question that can we have a similar protocols, but without this homomorphic commitments, because we could instantiate them with hash functions and basically have a post-quantum secure ones. So I was working at some moment on isogeny-based protocols. We wanted to build threshold protocols based on isogenies. Then we started to focus on solve it, and then we got this concept that called zero-knowledge proofs over secret shared data, introduced by Boneh et al. So here is a little bit different from the zero-knowledge proofs, because in zero-knowledge proofs we have one prover and one verifier. But here we have one prover and multiple verifiers. but not only the witness is hidden for parties, but also the statement itself is hidden, but you know a piece of it. So you can look at it as a share of it. So here, again, we have this security properties that we have a proof system. We usually want that honest prover will convince the honest verifiers. It's called completeness as before. So we have a flavor of soundness, which is stronger than the one that we have in proof systems, because here we want that not only a malicious prover, but up to T malicious verifiers even cannot collude together to convince these honest verifiers if the statement is not correct. So, and here we have a slightly weaker notion of zero knowledge, which in zero-knowledge proof systems, we usually say that if the verifier is malicious, you cannot learn anything about the witness. But here we say that up to T of those verifiers cannot learn anything about the witness, and also about the main statement is X. So this is something. But you see that it's quite similar to the VSS that we want to solve. So the positive result that Bonnet et al. Shows that we can build these protocols in the honest majority setting. So then it's a natural question, can we build this proof system for Shamir? We did so in basically AsiaCrypt 2023. So, but our focus was really on post-quantum security and proving that this protocol is secure in the basically random oracle model, post-quantum, let's say quantum random oracle model, because we wanted to revisit isogen-based protocols. And here is the basically performance of our protocol. So Feldman, as I mentioned, requires high entropy secret, but Peterson and ours works with low entropy secret as well. So ours is in the quantum random oracle and requires basically hash operations and polynomial operations, basically very, lightweight. We showed in the implementation also that this is considerably faster in verification, sharing, and reconstruction, and post-quantum secure. But this was mostly the reason that I started to develop this idea even more. So we had a little bit higher communication compared to the previous ones, but this was something that I was interested because Peterson could achieve perfect simulatability, but with hash functions, you never can achieve this. So yeah, the first contribution of this paper basically is generalizing this idea of AsiaCrypt and optimizing it slightly and presenting a general construction, which we refer it to pi. Usually in crypto, we refer to protocols pi. So, but also pi in Turkish is basically means share, and that's the reason that my mother tongue was Turkish, and that's the reason I used it. So for sharing, if we do as Peterson, we do twice Shamir, but different from Peterson, instead of committing to the coefficients of the polynomial, so we say that, okay, let's just commit to the evaluations of these polynomials. Then we use another randomizer that it's just random value, gamma I. Then you send it to the random oracle, doesn't need to be a quantum random oracle, but general, just random oracle, like as Schnorr, you see, it's similar to Schnorr. So then you open this ZX, which is exactly extension of Schnorr, you will see in the rest of presentation. Randomizer polynomial plus D times D is the challenge, and this secret polynomial that you used for Shamir. And then you publish this as a proof. So this is a non-interactive Tirschel zero-knowledge proof. And then given the shares, Fi's and gamma I's, so basically parties get involved in the verification. They first check that degree of this ZX polynomial is smaller than T, smaller or equal. So this was hidden in the Feldman and Peterson because they had just this T+1 commitments. So no one cared if it's bigger than T+1. Just they started to check this verification, and you already needed to have T+1. But then you need to compute this D from this proofs, like as the proof generation, and then you start to check your associated to you, this commitment was computed correctly. So we have this CI, so you have Fi as a share, gamma I as a share, so just you need to extract this Ri, and you can extract Ri from evaluation of this ZX in point I, and then subtracting D times your share. So this is exactly what we do. So here. So then if there's a complaint similar to the Feldman and Peterson, so you start basically to raise, and the dealer opens and the others checks, and you get to some consensus who is malicious. Reconstruction again is similar to Feldman and Peterson, but the only difference is that we use our verification algorithm to check that these shares are valid. And basically everything is as before. So you collect T+1 valid and you reconstruct the secret. So this is the general construction that if the secret that you want to share has already enough entropy, so Fi's also have enough entropy, you don't need to use gamma I. But the point is that if you use gamma I, this is not a general construction, so you have to separately prove, because we prove the security for general one. We will see in one instantation that once we remove it, we cannot anymore argue that this vector commitment is hiding. So yeah, we proved this theorem that if this basically commitment is a vector commitment and so it's a secure commitment and we have a random oracle, so we show that it's a secure VSS that achieves the properties that we define in the paper for VSS. Basically, it's the one that also achieved in Peterson and Feldman. So we're starting to instantiate. So exactly this is the point that we instantiate this commitment first by vector commitment of Peterson. So this gives an alternative to the Peterson VSS. We call it pi-p. So similar to the Peterson, now this can achieve perfect simulatability. So basically the comparison of HCrypt paper with Peterson was comparison of sort of apple with orange because that was used hash functions and that was using discrete log-based things. But it was first time, so we hadn't any alternative to compare. So then the second instantiation is just using hash functions. So basically you have a vector commitment based on hash. So you achieve something which is quite similar to our HCrypt paper, but constant times improvement in all metrics. And this one is also computationally simulatable rather than perfectly simulatable. So now we have this instantiation that I mentioned that I removed this randomizer gamma I. So if you remove it, it's not anymore perfect. I mean, hiding commitment formally. So this is the reason that we proved that it's similar to the Feldman. It is unpredictable, which is a weaker notion compared to simulatability, which basically means that you can learn the secret in exponent, but you cannot extract it. Basically, you cannot recover the secret like a discrete log. And this requires high entropy secret. So I just instantiated with discrete log-based and hash-based commitments, but go ahead and instantiate with lattices, isogenes, codes, whatever you want, just random oracle plus commitment. So here is the performance now. The comparison is with apple, and so you see that they both require high entropy secret, but it was in the plain model, but this is a random oracle plus discrete log. Now the cool thing is that we increase, of course, the sharing time by constant factor and communication slightly, 2-3 times. But this is the interesting thing because we improve by factor of t the number of exponentiation in the verification. And usually once you build a distributed protocol based on VSS, so you are playing as a dealer once, but you are verifying for n-1 parties. So that's the reason that why we improve by factor of n all these distributed protocols like as Peterson DKG. So the Peterson as well, I mean, you improve by constant factor, and then our HCrypt again by just constant factor, but here by factor of t. So here is the performance of new protocols. I mean, we compare Pila, I call it Pila because it means share it. Pila with our HCrypt, as you can see that constant times improvement in everything. And this is the pi-p compared to Peterson. So you see that for large number of values, for example, verification is almost 100 times faster at the cost of 2 times, I mean, just 1 time slower sharing and slightly higher 2-3 times higher broadcast communication, but the private communication is the same. So the codes are publicly available. Check it out. Even in your phone, you can run it because it's an online terminal and it runs automatically. So I was interested to see how much overhead we added to Shamir really to make it verifiable, and that's interesting to see. So for more than 100 parties, it's almost just doing twice Shamir. So basically means that you do twice Shamir, you sacrifice one to achieve verifiability in others. So then in the rest of paper, I got interested to achieve public verifiability on at least one of those protocols. I mean, we cannot achieve in hash-based one, but I tried to achieve in this pi-f. And to do that, I started to basically think about intuitively what's happening. So in VSS, to be honest, if you want, I mean, just say what's the idea behind VSS is just doing Shamir and giving a non-interactive Trichot-Zeroange proof for this relation. So basically all the protocols of Feldman, Peterson, and the ones that I mentioned are just a non-interactive Trichot-Zeroange proof for Shamir relation. So, but in this case, unfortunately, we have this happy and unhappy path. So you have to interact. Basically, if there is a complaint, someone raises a complaint, so you have to publish, I mean, dealer, and then the other check. So this is the reason that we have a happy and unhappy path. So in all these protocols that I discussed, we have this case. But PVSS tries to solve this problem by saying that not only you prove that you did this secret sharing correctly, but also you prove that you encrypted the basically shares under some public keys, and you publish this proof. And this proof now is not non-interactive Trichot-Zeroange proof, rather than just a standard non-interactive Zeroange proof. So basically, it's a publicly verifiable. Everyone can check. That's the reason that basically in PVSS, this primitive, you need to register your public keys as a party, but that's cool. Basically, you don't need DKG. So you can just register your public key. And the cool thing is that it requires one round. And in literature, usually PVSS schemes, categorized in two family that usually the secret either is F0 or G power F0. So here I will focus on the second one. So to turn this pi f basically to the publicly verifiable secret sharing, so I first started to think about generalizing this discrete log problem because we use this one for security proofs. So we generalized the discrete logarithm problem over polynomials, and we called it polynomial discrete log problem, which basically says that given, let's say, evaluations of some secret polynomials in public indexes xi's, from I to n, and n should be bigger than the degree of polynomial, of course, because any degree T polynomial gets unique with T+1 evaluation. So then you cannot extract this fx. So you can see that discrete log is basically a special case of this one once basically the degree of polynomial is just 0, because it's just constant term. So now we show that basically in the rest, this polynomial DL problem can be reduced to DL. So it's tight also. So then we generalized the Schnorr protocol and we presented the sigma protocol, and it is also proof of knowledge that you can prove the knowledge of this fx. So now we want to use this sigma protocol. So we had this pi f, so which is verifiable version of Shamir. Now we want to move it to the PVSS, which you can extract just G power F0. And to do so, we assume that the public keys are given to the dealer. So basically, you as a dealer just get these public keys and start to do Shamir. Then you encrypt these shares FIs by public keys of parties. So, and at the rest, you start to use this proof system. And for that one, you remember in Schnorr, we have this G power R. So now exactly we have this public keys power Ri. Then you have this challenge, and then you open this opening. It's like as pi, you see. And then you open this proof system, and this is now publicly verifiable. Basically, anyone can check that this, given the public keys and the encrypted shares and this proof, so everyone can check just this equation, and degree of the x is smaller than t, and d is equal to this. So this is, we prove that this is a basically secure PVSS scheme. And in the reconstruction, so basically you need to decrypt. So using your secret key, you need to compute this ciphertext power 1 over secret key, and then give a proof using Chow-Peterson DL equality proof that you did this decryption correctly. Once we collected T+1, we can do Lagrange interpolation, but now in the exponent, because this grade log has this homomorphism property, so you can do it in exponent. So we prove that this is a secure VSS, basically the properties that we want. And here is the performance of basically this pi s. After printing just the paper, a day after that, I noticed that this construction was hidden in one Albatros paper by Bernardo David and Ignacio Cascudo. And I just then checked their paper. I saw that there are some small issues in their security proof of their Sigma protocol because they don't introduce this problem at all. And I think it's necessary to prove the security of that Sigma protocol. And that's the reason I kept it here. So interestingly, independently, recently, this Doc network, this blockchain company has implemented both PyLa, this hash-based VSS, and this PyS in, Rust, because my implementation was in the SageMath. So if you're interested in fast implementation, go with this ones. So this is the performance reported by them for PyS. So you can share 100 secret by 100 parties in less than 25 milliseconds and verify it. And the proof for 100 parties is less than 2 megabytes, even 1.5 megabytes. And they mentioned that this is useful for blockchain because it's publicly verifiable. So to wrap up, so basically we proposed a general and simple construction to build a verifiable secret sharing. And you just need a commitment and a random oracle. So as I mentioned, it's general enough to be used in lattices, isogenes code, or whatever you are working on. And the new VSS schemes can be basically replacement, for the old ones, Feldman and Peterson, especially that usually once we use Feldman, we already have random oracle in the protocol, so you don't add random oracle, because of just this. And as I mentioned, basically this PyLa is post-quantum secure, and synthetically only 1 times is slower than standard Shamir. And the new PVSS scheme PyS can be used in also various applications. We already used it to revisit some protocols from Crypto 99 by Schoenmaker. So the paper, we have also a new e-voting protocol based on them. The paper will be presented in Munich in ACNS 25, and it's available here. So something that I would like to highlight at the end, once you want to use these protocols, to be honest, you need to know a little bit Zero-Hash proofs. And because these proofs, you may notice that Feldman has one hidden property, and that commits to the secret for free, because this commitment to the main first coefficient is commitment to the secret as well. So you don't have this here because we just commit to the evaluations of parties, but it's easy to achieve. So basically just commit to the main secret as well. So we have done this in our ratio creep paper for one hash-based one, and also here we did similar things. So I see that many times you need this commitment to the secret because it's helpful. So you can just easily, by modifying and adding one commitment to all those protocols, you can achieve this. But I didn't discuss in the paper, but you can do it easily. Thank you very much.
Yeah, well, thank you for your talk. Are there any questions?
They want coffee.
Yeah, I guess we're slightly over time. So if there are no questions, let's thank Karim again, and indeed all the speakers in the session.